Well, I kind of like how our textbook splits loops up into two chapters. Because then when the course shell was put together for SDEV 120 across all the different Ivy Tech courses, that was split up across two modules. So we introduce loops and then have a couple days to think about it before we get to the second week on loops. And hopefully you realize that now we're ready to produce a full piece of software. Right? Everything we've done so far, we have that start, it does a bunch of stuff and then it ends. If the user wants to do something else, they have to start it again. Well, now we're ready to let the user open the software and do things until they're finished, and it's just going to keep loop's going to control that. And when the user's finished, then the software closes. So more of a full piece of software. So that's what we're going to look at today, controlling software. I'll put that for the label. A couple other things. It's going to come mostly an example. And there are a few different things I'm going to mention. Two that I would like to do, so I might have to move one of them over to a supplemental video. But let's kind of look at the agenda for today now. So the example I had in mind today is a networking thing. We're going to ask the user how many machines they have on their network and generate a bunch of random addresses for them. And we're going to store those and bring them back in. So kind of a full piece of software. Instead of just doing one little thing, we have a bunch of things that we need to do. Well, like I said, random network addresses. So we're going to look at random numbers. We'll get that. And then we'll look at control structures. How do we control our loops? And there's several different ways we could do this. Obviously, we could just have a counter and keep track of how many times it runs. We could use what's called a Sentinel Value, a number that doesn't make any sense. So like we're going to ask for people's ages, and we have a bunch of them. It's like, please enter an age, and when you're finished, enter -999. That's never going to be entered as an age, so whenever the user puts that in, we know they're done. The book has some examples of those. I might do an optional video covering those. They should be fairly straightforward. Just count an extra variable to count how many times things happen, or we control our loop. We know we're finished when the user enters a number that just doesn't make any sense in our setup. Those might go in an optional one. The one we're going to look at mostly is a menu-controlled loop. We're going to give the user a menu, and they'll choose an option from that menu, and that'll keep the program running until they choose the exit option. Personally, so that's what most of the examples are going to be like. But personally, I feel that's a little out of date. So I'm going to expand that and after we finish, change it into event-driven. I should put the word driven here. So we're going to look mostly at menu-driven, and then we'll modify it to event-driven, and that might be put in a separate video. But the same example, just modified. So here, we're going to give the user an option, like option 1 is to set up, get a bunch of addresses for a network, and exit 6 is exit or something like that. Whereas event-driven programming, that's with the GUI, the graphical user interface, where we'll give the user a bunch of buttons and they can click on those. So a little bit more modern. It's not included in the course curriculum here, so it's not a requirement. But I always feel like that's probably the one you want to know, right? We want to give the user an interface where they can move their mouse around and click on things, not necessarily a menu-driven one. So I'm going to include those, and we'll do the same example. So we'll need to look at some random numbers, and following a trend of switching up, doing plans in different manners each week, I'm going to do the plan with some UML diagrams. Which, by the way, if you want to do your planning the way we're going to look at today with UML diagrams, I would accept that in place of pseudocode. Because it'll kind of have the same effect as a pseudocode. breaks down and describes what's going on in the program without being the actual program itself. The main difference is UML is the international standard of communication. Pseudocode is just a tool that's kind of personal to each one of us that helps us organize our thoughts. So if you would rather use the international standard of communication, like our planning is going to be done today, I will accept that instead of pseudocode. So a few things to go over, mostly examples. We're going to build one big example and talk about these things along the way. We're going to talk about random numbers, menu-driven stuff. That's kind of an extra one, but it's not included in the curriculum, but I really feel like people want to see that, right? You want to know how to make buttons the user can click, not just some words there. That way your software doesn't feel like it belonged 50 years ago. Something a little more modern, still basic, still starting out, so not super fancy interfaces, but at least a box we can click on. Some colors and things. And then we'll do our planning with Uml diagrams to introduce a couple more of those, which the ones we're going to see should have been covered in the Zoom meeting on week 4 or 5. I haven't wrote down but we'll talk about those in the Zoom meeting, so hopefully they've shown up before this video falls into place, but I'll do at least a quick review on the 3 we're going to look at. All right, so let's get started. I'll erase this and jump right in here. Okay, so we're also going to use this example next week when we introduce arrays. So it's going to be reused several times, our menu-driven programming, then we're going to rewrite it for event-driven programming this week. Then next week we'll use it for arrays. So, well, for one, that means when we go to save it, I'm going to give it an actual name, not just mash the keyboard. I think some people have indicated that bothers them when I name files like that aren't going to be kept around. I used to name all my files like that. It's mash the keyboard, and I keep track of them by date. But in front of a classroom, that seems to bother people a lot. So anymore, I only mash the keyboard for a name on stuff that's not going to be saved. It'll be deleted very shortly. But today's example is going to have an actual name. So we're going to generate some random network addresses. That's what we'll need first off, is random numbers. So they're not truly random. It's a complex algorithm. It's going to scatter values around and give us a different value every time. We can kind of count on that. But it is an algorithm. It could be predicted what number is going to be generated. And sometimes when testing and debugging, we go ahead and make a little change to that algorithm so that we do get the same number every time and can run all our tests and make sure other parts of the program are working consistently. But pseudo-random is what we typically call it. We can't really have random in something like a machine. It's just a very complex algorithm that scatters our numbers all over the place, so it seems random. And then we can get into a big philosophical debate of, is random even possible? Is the universe deterministic? Right? Random might not even be possible in the entirety of existence. So definitely not in computers. But we're going to call it that and act like it is. The numbers are scattered around enough. They're going to seem almost arbitrary when we ask for a random number. And when we ask for a random number, those complicated algorithms will go in and the computer will generate some number between 0 and 1. I drew the wrong symbol there. Some number between 0 and 1. So a floating point number, 0 will be included, 0 can be included, 1 will not be included. So including 0, but not including 1, there's some number in that range. So we could make use of that. We could just ask for a random number and say, is it below 30%? Or is it above 80%? Something like that. But usually we want to modify that a little bit. We want to work with integers. That's easier for us to think about for most people. So to turn this number between 0 and 1 into a random integer, let's talk about a deck of cards, 52 cards. So we want random numbers somewhere between 1 and 52. So when we ask for a random number, we get something between 0 and 1, which includes 0 but does not include 1. So to make that range bigger, well, we need to multiply it. So we take that random number we have and just multiply the whole thing by 52. So 52 times 0 is still going to be 0. And, well, multiplying doesn't change the equality in this one or the inequality in this one. So now we have a random number between 0 and 52, which includes 0 but does not include 52. And these are floating point numbers. We started at 0 point blah, 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 some really, really small number, and we made it bigger. So we still have that decimal and all that other stuff in there. So to get that to integers, we want to floor that number, the thing we just had. 0 is less than or equal to x, which is less than 52. And that will give us, it's going to cut off the decimal point. So 0 point something, that decimal and all the mantissa cuts off, and we get back just the integer 0. And over on the other side, the 52, well, it doesn't include the 52, so it only goes up to 51.9999999, just right below 52. So when we cut that decimal part off, then we get back to a number between 0 and 51. And if we wanted to use 1 through 52 again, then we could maybe add 1 afterwards, because this, when we floor it, gets us a whole number between 0 and 51, inclusive on both sides. So if we add 1, that would get us back to 1 to 52. So that's the idea of random numbers. We'll do that a lot. When we ask for a random number, we get some floating point value between 0 and 1, which includes 0 but does not include 1. So then we multiply it by however big we want to make it, and then we floor it so that we get back to just the integer part, which means our larger size is now 1 less, because, like in this case, 52 means less than 52, means that only went up to 51.9999999. So right below 52. So when we cut that decimal off, we're going to be at 51. And then we add 1, and that'll give us a number somewhere between 1 and 52, inclusive on both sides. So that's kind of how random numbers work. Just ask for a random number, multiply by whatever size you need, then floor it, and add some back if you want to adjust your range. You could stop at this point and then have like 0 to 51. That works. That'll work just as well. But that's how random numbers work. So we'll use that to generate some random network addresses and kind of make a program that keeps track of the machines on the network for us. Okay, so one more quick example on random numbers. This is the only time we're going to talk about them. So repetition is important in learning, so I want to go over at least 2 different things. So first, a second example here, maybe a set of D&D dice. That's something a lot of people are familiar with. Playing D&D seems to go along with being a computer person. But analyzing that would be an issue for a psychology person. We can just take note of it. Like when I'm making these videos, this is the weekend that your project proposal is due. So I haven't seen them yet, but I will be really surprised if there's not at least one person that wants to make a D&D game. Or at least a small portion of a D&D game, because obviously that could grow very, very large, more than a 1 semester project, but at least get started on some stuff, a couple little quests. So a lot of computer people are familiar with D&D. The dean for our school here keeps a set of dice in his office. He asked me to mention that whenever people turn in D&D stuff for their projects. But what's a good one? The 20-sided dice. So we want to quickly simulate the 20-sided D&D dice to see if something's going to happen or not, right? For those who are familiar with the game, if you're not, we're going to simulate rolling a dice with 20 sides and determining that. So first thing we need is a random number. What did that roll come out to? So I'm just going to call it R because I'm on the chalkboard. If you were typing this out, you'd probably want a much more descriptive name. But R is going to equal some random number. And that'll give us this, a floating point number between 0 and 1, which includes 0 but does not include 1. But we want a 20-sided dice. So we need to take that number that's between 0 and 1 and turn it into something between 0, turn it into 20 integers we can use. So then R will be reassigned whatever is stored in R times 20. And that'll get us from 0 up to 19.999999, however many digits the floating point numbers are carrying through, but we'll be right below 20. It'd be nice to work with integers, so then we can reassign R again and floor whatever is in that value R. So the 0 point something, that decimal fractional part just cuts off and we go back to 0. So this gets us a number between 0 and here we were right below 20, so when we cut off the decimal part, we're going to have 19. So that gives us a number between 0 and 19, which is 20 sides. We could check those, but since we're talking about a dice, typically dice, when we go to roll a dice or a couple dice, there's not a blank side on a single die, right? Our smallest value is going to be 1. So putting the code together would make a lot more sense if we started with 1 instead of 0. So then this thing that's somewhere between 0 and 19, we can add 1, and now we'll have something between 1 and 20, the sides on the die. So once we have that, we can just check and see what the roll is. Go back to our if statement. So like if R is equal to 17. Just for one quick example, we could check any number. I'm out of room here, but if R is equal to 17, then we'll do a bunch of stuff with our regular selection structure. And we'll do the stuff that would have corresponded to rolling a 17. So just a second example of how that works. We ask for a random number, multiply it to get to the range of integers we want, and then floor it to get back to just the integers without the floating point. And if it makes sense to do so, then we add 1 just to go from, like in this case, 1 to 20 instead of 0 to 19. We could work with 0 to 19. That's still 20 values. It's just if we're thinking about the roll of a die, we're probably going to think about 1 to 20, not 0 to 19. So this part, the +1 is optional, just if it makes more sense in that particular situation. So a second example of random numbers, hopefully that makes sense, and we're going to see some more random numbers when we get to the actual example for today here in just a few minutes. Okay, another piece we'll need in today's example. So I said we're going to generate a bunch of network addresses. We probably want to keep those around. So we're going to finally see how to store values, how to keep them around in storage, not in RAM. So it'll make more sense when we see it in the example. I just wanted to talk about it here. So far we've had these, flow charts. Might have a couple branches, some loops, different things, but somewhere down there we'll have our output block, which thus far has gone to the console, right? When we see this, that jumps over to the console and writes out a bunch of words on the console. That's supposed to be the computer screen. Yeah. So it jumps over, puts it on the computer screen, and then we're done with it because everything we've seen so far would have been done with our volatile memory storage. So it's only in RAM, which means when the program hits the end, RAM's going to be cleared out. So it's gone once it goes to the screen. But we might want to do something different with it. And I decided to use the pictures today because, well, the book has it in words, but when we make a plan, we're going to be using pictures. So I thought I'd start drawing these, at least some quick reminders. We have our volatile memory storage is volatile storage is a rectangle. Our IO, in, out, is parallelogram. We've seen some of those symbols. Probably have a decision made somewhere along the way for different branches, or maybe even a loop. We do that a lot more than recursion, so probably have a selection structure in there as well. Another thing we could do is when we get over to the hard drive, storage. So our symbol for storage looks like this. The UML symbol for storage is supposed to be a stack of tape reels. Right? You've probably seen really old movies, the machines that use reel-to-reel tape. The symbol for storage is a stack of those. So at some point we want to come over here. So there's a pre-built function we can call, which I'm going to use the symbol like Raptor does. So remember, the official UML symbol for a call, or invocation, is a rectangle with double walls on the side. But that can be confused with this one quite easily, so this symbol is sometimes used as well. In the software we're using, we go with this symbol. But those mean the same thing. So we're going to call this pre-direct thing to redirect our output. We're going to redirect our output, so instead of going to the screen, we want it to go over to volatile storage. And then we'll store it and keep it around. And then on the next run of the program, we might have our little input block, and instead of asking the user for the input, once again, we can throw in a call statement and redirect our input so that instead of coming from a user out here, instead of coming from our user, we're going to redirect that so that it comes from storage. And that's how we keep things around. We call this redirect input or redirect output function to read from storage or write to storage instead of asking the user for it. So we'll see that here in a few moments and kind of some quick pictures because our plan is going to come in pictorial form today. So our invocation statements are going to look like this. Remember, the official one looks like this. So if you see a rectangle with double walls, that's the same thing as we're using this big arrow for in class. In, out is parallelograms. Volatile storage is a rectangle, and selection structures are a diamond. And loops make use of selection structures, so diamonds also show up in loops. So that's our pictures, just a quick review of those, and the preview of how we send it to storage and keep it around instead of just being done with it when we get to the end of our program. We'll see that in the actual example here in a few minutes. Okay, so now we're ready to go over stuff about this label I put on here. We want to control going through software. I put controlling software instead of just loops because now that we've seen loops, well, we're going to create a main loop for our software so that it doesn't just start, go to the end, and if the user wants to do something else, they start it again. We're going to have a main loop that starts and keeps running until the user is finished with whatever that piece of software does. So we need some ways to control that. And there are 3 right up in the book, and one that is what we use 99% of the time in the modern world. It's not mentioned in the book, so I want to cover that. So the first 2 should be fairly straightforward. If you have questions about them, we can go over these in the Zoom meeting, but it should be straightforward. So like we have counter control. we set up a variable, we started at 0, and every pass of the loop we increment by 1, and then once we've done our loop, say 12 times, we're finished. Like, how many times is the loop going to run? Just a simple counter. Just set up a variable and count how many times the loop has occurred. The next one is called Sentinel Control. So, like Sentinel, traditionally that word means like a guard. Something's going to stand there and watch. And that's going to be a value that would not be used as an input. So if we ask for ages, we can have them put up in the prompt, enter a negative number when you're done. So a negative number doesn't make any sense as an age. So as soon as the user enters, they're going to keep typing in the ages, 23, 37, 58, 4, 12, 93, a bunch of ages, and then when they're done, they put -1. It doesn't make any sense as an age, so we'll watch for that, and we'll have a selection structure that says if the value or the control for our loop will say if the input is less than 0, we're finished. So something that doesn't make any sense. Or if we're going to ask for names, ask for a list of names, and it's safe to assume that there's not anybody named Quit. So we're going to say, in the prompt we'll say, enter the next name, or enter Quit when finished. And then whenever the user types in the word quit, well, the computer is going to know that we're finished entering names at that point. So that's what a Sentinel is. It's just a value that we can check for that's not going to be one of our normal inputs. Those should be fairly straightforward. If you have questions about it, let me know. We'll go over it in the Zoom meeting. The first one we're going to talk about today is menu-driven. And this is where we give the user a bunch of options. So like our prompt will be something like enter 1 for names, 2 for ages, what else is there? 3 for towns, and collect some data about people, and more than one person. Everything we've seen so far, we just collect that data from about one person, then restart. So we'll go into a loop and ask the user, push 1, 2, or 3. If they enter 1, they're going to type in a name. If they enter 2, they're going to type in a bunch of ages. If they enter 3, they're going to type in a town. And eventually somewhere down there, I'll just go ahead and put it 4 to exit. And eventually the user will type in a 4, and the software will be finished. So that's the basic idea of menu-driven programming. We're going to give them some options, and the user will select one of those options for what happens next. So that's what our example is going to look like. We're going to put this example together with a menu-driven one, and then we're going to come back and look at event-driven programming. At least the basic concepts, because this feels really out of date to me. Big software hasn't used menu-driven programming in a long time. Like about 89, 1990, I was kind of finishing up menu-driven programming. So that was when I was about 12 years old. So to me, it's like, okay, feels pre-teen. And I'm well into middle age now. So the stuff that I haven't used since pre-teens feels very, very out of date. So I'm going to do the modern one, at least talk about it. This is probably what you want, event-driven. That way it doesn't feel like your stuff belonged 40, 50 years ago. And event-driven is when an event happens. Something happens. The user pushes a key. The user clicks on the mouse. Things happen, and then we respond to those things that happen. So we're at least going to take a quick look at it. We're not going to get very thorough because it can be a little more advanced than the level we're at. But we'll at least start and maybe draw a box, and we'll call that box a button, so that if the user clicks the mouse inside of that box, something's going to happen. Or in this case, we modify the program and have 4 buttons, one of them labeled exit, the other 3 labeled to do stuff, and the user clicks on that rectangle, something happens. It would be the same as typing a 1, 2, or 3 in a menu driven. We'll see that in a minute. That'll probably come in the second video. This first video, we're going to put together a menu driven program that tracks network addresses for us. So I'm going to erase this and let's start putting the plan together. And today's version of planning is going to use Uml Diagrams, the International Standard of Communication. So if you want to do what we're getting ready to do instead of pseudocode, that is fine. I will accept it. Because pseudocode is a personal tool to help you collect your thoughts, to put things into a computer, whereas UML is an international standard of communication for IT. So probably a little more important to know that is the way I feel about it. And if you're a visual learning person, then UML is great because then you're doing everything in pictures. So I'm going to erase the board and then let's get started with the plan for today.